Log on, tune in, find out. Another good idea from Cambridge.
Okay, so let me recall the setting we used yesterday. G is semi-simple Lie algebra. Then I have fixed an important element. This important element gives rise to an SL2 triple. Which gives rise to Losev slice. However, I don't want to consider the Losev slice as a subvariety in G. I want it as a subvariety in G dual. So this is embedded into G dual. And E goes to chi, which is pairing with E with respect to the Killing form. And also I have a homomorphism from one-dimensional torus to G, which comes from the SL2 triple. And I define Kazhdan action T applied to some point alpha is T2 minus 2 gamma of T alpha. Here alpha is in G dual. And this action gives rise to a grading on to the grading on the Losev slice, and this grading is positive. And also yesterday we had a Poisson structure on the algebra of functions here. And I start today giving an alternative definition of this Poisson structure. And to do this, so our first goal is to represent S as a quotient of some symplectic algebraic variety. So among all Poisson varieties, symplectic ones are most nicest. Okay, so to do this, I first need to consider the cotangent bundle of G of the group. So here G is algebraic group. With the algebra G. And I will identify this cotangent bundle with product of G and G dual. Well, here for G dual I take left invariant forms. Now I have two actions of G on this variety. First action by left translation, let me call it left action. Well, G applied to the pair G1 alpha is just GG1 alpha. because our forms here are left invariant. And now I also have right action, or more precisely, action by right translations, which is G applied to the pair G1 alpha is G1 G2 minus 1, G applied to alpha. Okay, now what else? I have the canonical symplectic form. Let me denote it by omega tilde. And of course, being canonical, this form is invariant with respect to both these actions. Okay. And finally, let me define a Kazhdan torus action. T applied to G alpha, or G1 alpha, is G1 gamma of T to minus 1, T applied to alpha. So on G dual, this is our old Kazhdan action. And here this is just some twist. And in particular, let's note that this action commutes with left G action but not right one. Okay. And another remark is that this action, this Kazhdan action, multiplies this canonical form omega tilde by T squared. So why? Well, actually, this Kazhdan action is somehow composed of two parts. Its usual action by fiber-Wass rescaling, this T2 minus 2. And then right action of this gamma of T. So right action leaves the form invariant. And rescaling by T2 minus 2 multiplies this form by T squared. That's how we get this formula. And now, so I wanted some symplectic variety. And this symplectic variety is constructed as follows. So by definition, equivariant Losev slice I denoted by X is just a product of G and S considered as a subvariety in the cotangent bundle. Now, let's see. So what structures do we have on X? Well, first of all, we have a G action. And this is usual action, this is usual left action. So G applied to G1 S is GG1 S. Then we still have this Kazhdan-Torah section. So Kazhdan action restricts to X basically that's because S here in G dual is stable with respect to the Kazhdan action. And now, so we also know that this Kazhdan action contracts S to a single point, but here now it's no longer true. But still, sort of this claim is true. This action contracts X to orbit Gx, where X is 1 chi. And so contracts here means something. Let me draw a picture. So somehow if this is my X and this is Gx, then contraction is something like this. Now I promised a symplectic variety, so I need to introduce symplectic form on X. And we have an obvious candidate for it. So we put omega to be restriction of omega tilde to X. Now let's see. So this form is definitely closed. It's definitely G invariant. Kazhdan action, so sorry, tilde here. Kazhdan action definitely transforms this form like this, because well, that's just a restriction. The only thing we need to check is that this form is non-degenerate. Well, we have our distinguished point X here, and one checks directly that omega is non-degenerate at this point. So you can write down this form actually explicitly and check this. Now this form is G invariant. So it's non-degenerate on the whole orbit, Gx. And, well, finally, this contraction property shows that it's going to degenerate everywhere. Which one? Why?
The last
Well, somehow, if you consider the set of all points where the form is non-degenerate, this set is open. This set is open and G-invariant. But now this Kazhdan action does something like this. So it definitely moves any point to this open neighborhood. Okay. So we get this symplectic variety with action of G. So our algebra of regular functions has G invariant Poisson bracket. It's well known that any symplectic variety has a natural Poisson bracket. And now we just restrict this bracket to G invariants. And we get a Poisson structure on the algebra of functions of Losev slice. I'm not going to explain why this structure coincides with yesterday one, maybe in discussion session. But anyway.
The contraction of the torus on the orbit on the first factor multiplying by gamma of t inverse.
Yeah, so it somehow moves us to somewhere, but well, I mean, so the point is this. So let me say it like this. So the set of G orbits, which is S, honestly contracts to a single point. That's what I mean by contraction.
Okay, but the first you said contracts. Okay.
Well, okay, let me put it in parentheses.
Okay.
It's not pointwise contraction anyway. So now actually, why do I need this X? And the point is that I'm going to consider quantization problem, and it's known generally that quantization problem on arbitrary Poisson varieties, even on Poisson affine spaces, is very difficult. It was solved completely by Kontsevich, but his procedure is extremely difficult. Now, symplectic varieties are much easier to quantize. Quantization was established in perhaps 80s, and I'm going to use one of these constructions, which is due to Fedosov. Okay. So now our setting now is the following. So we have X, it is affine algebraic variety, equipped with fast G action. Second, action of a torus. And these two actions should commute, like in our case. And second, and finally, and probably most importantly, symplectic form. So omega is symplectic form. And it should be G invariant. And it should be, well, not invariant with respect to the torus, but rather it should be rescaled. Sorry, by the torus. For example, well, what are examples? X here is an example. Or the cotangent bundle above is an example. Okay. Now, so Fedosov quantization is deformation quantization. And let me explain you what deformation quantization is. So what we are going to do, we are going to construct what is called star product. A star product will be a map from the tensor product over C of algebra of regular functions to formal power series with coefficients in this space. And, well, there is a very stylish notation for indeterminate is h bar, which in physics is Planck constant. But anyway, here it's formal variable. Now this map, let me, well, one can write, of course, f star g is sum from I equal to 0 to infinity di f g times h bar to the I. This should be subject to the following axioms. Well, first axiom is that the star product should be associative. Well, more precisely, its extension is ch bar linear extension to this tensor product? Well, that's a natural extension, I mean. So the more or less the only way you can extend. This should be associative. And a minor requirement, which is also should be put here, is that 1 in Cx should be a unit. That's the first one. Then one called compatibility. And it says that the star product is compatible with the structures we already have on our algebra. So what structures do we have? We have usual commutative product, first of all. So this f star g should be congruent to fg modulo h bar. So in a sense, this star product is deformation of our usual commutative product. So the right way to think about it, this is just formation parameterized by h bar. But the only point is that this series is not necessarily convex. So we want to make this formal. And here, also another requirement, we have Poisson bracket. And we want our star product to be compatible with this in the following way. Well, we can consider f star g minus g star f. So it has no constant term. And it starts then with h bar bracket of f and g. Okay, that's still not all. We have the set axiom, and this is called locality. And here locality means that all di's are bidifferential operators. I don't want to give a precise definition what a bidifferential operator is. Let me just explain what this condition allows us to do. So first of all, we can, of course, if we have some open subset in X, we can restrict our star product to this open subset, or more precisely to the algebra of functions on the open subset. But we can do even better.
Why is there no constant term in compatibility?
Here, because, well, up to h bar, the star product is commutative.
But saying something about the d0 of fg?
Yes, it says that d0 is just a product.
Oh, okay. But that's not part of the data that follows from the...
Yes, that follows, I mean.
Oh, okay. Sure.
And, well, here we can do even better if we have a formal neighborhood of something in X. We still can restrict this star product to this formal neighborhood. Because differential and so bidifferential operators can be restricted to formal neighborhoods. Say to formal neighborhood of some point.
Is
for
X
example.
supposed to be smooth?
Yes. So when I say symplectic, I mean smooth. Yes, thank you.
Sometimes you said Poisson. I wasn't.
So here, X is smooth, as it was in all our examples. Thank you. Now, these are usual axioms for star products on, doesn't matter, manifolds or varieties. But I also have two group actions here. Action of G and action of C times. And I, of course, want my star product to be compatible with these two actions.
So does it mean that locally this embeds inside equivalent differential operators? Or is it what you mean by locality?
Locality. Well, say it again. I mean.
So you mean that if you take local, if you take something like T star of an open subset of the affine plane, affine space, and you quantize that using differential operators, you want your DIs to be inside this ring of differential operators. Look, is that what your locality means?
Yes, more or less. Okay. Okay. Now compatibility with actions. Means the following. So first of all, all DIs are supposed to be equivariant maps. So it's a map from Cx times Cx is G equivariant that's compatibility with G action, and then compatibility with C times action, which is that di decreases degrees by 2i. So if you have two functions, f of degree k and g of degree, say, j, then di of fg is k plus j minus 2i.
Was your C bracket X positively graded?
Not necessary. Well, Cx, well, in this example with equivariant Losev slice, it is not positively graded. Okay, so these are axioms for a star product. And now, of course, I want something satisfying these axioms.
What does it mean degree? If Cx is not a polynomial ring, we can choose.
Well, I mean, I have a torus action. So I have grading and degrees computed with respect to this action. Okay. Now, what this Fedosov construction gives us it tells us that one can construct canonically a star product from so-called symplectic connection.
Just question concerning the degree di. It should be strict equality or inequality?
This is equality.
Equality. What about f is 0?
Well, as usual, it has all possible degrees.
So it means, so this equality means if the element is not 0,
Yes.
degree is enough.
Well, this can be 0, but then 0 has all possible degrees, so the statement is true for 0 anyway. Well, of course, you will ask me what symplectic connection is. And a symplectic connection, well, it is covariant, torsion-free. Or perhaps I should move torsion-free here. Derivative nabla. Well, it's connection on the tangent bundle. And now, symplectic means that nabla annihilates the symplectic form. What one should know about symplectic connections that such a connection always exists on affine varieties. And our varieties are affine.
The covariant refers to the group action or something?
Covariant is some terminology from differential geometry.
So nabla does not have to respect the group?
So let me say it. And moreover, well, covariant is just terminology, covariant derivative. And moreover, once we have two actions, we can claim, we can ask about compatibility with this action. And it turns out that moreover, one can choose nabla which is invariant with respect to both sections. And a remark here, unlike the usual Levi-Civita connection in Riemannian geometry, symplectic connection is not unique. There are many of them. But anyway, well, I don't want to say anything about Fedosov construction. So for me, it's just a black box. You plug your symplectic connection into this black box, and you extract your star product from a black box. And now I just want to consider some examples of this construction.
Just ask a question concerning the third condition. This is a stupid question. Why not all is why not always di are by differential operators?
For some stupid reasons, there are some gauge transformation and whatever this means. But if your gauge transformation is not differential, your transformed star product is not local.
So it means the third condition is a typical condition, right? Sort of.
Yes, in a sense. So in a sense, every star product on a affine variety is equivalent to this satisfying locality. But it's very convenient. Okay, I need to make one more remark concerning this. So we have whatever symplectic connection we have on a variety. So we construct different star products. But the point is that these star products are not that different. So namely, let nabla and nabla prime be two symplectic connections. And then I construct two star products, star and say star prime. Then the claim is this. There are differential operators T1, T2, blah, blah, blah on X, such that T equal to ID plus sum from I equal to 1 to infinity, Ti h bar I, is an isomorphism between star and star prime, which means that Tf star Tg is T f star prime G. So this is an example of this gauge transformation. And well, once we have group actions, so additionally, one can choose T to be, well, Ti to be G invariant, or maybe I should say equivariant, and of degree minus 2i. Why minus 2i? Well, I assume that h has degree 2, and so this t should be g times c times equivariant. So assumption that h bar is equal to 2. Okay. So that was about Fedosov construction. Let me explain some examples. Well, the first one is, in a sense, tautological, and this is example of while algebras. In a sense, it's not an example of application of Fedosov construction because Fedosov construction is based on this example, in a sense. So our X now is V, and this is a symplectic vector space. And then we have a symplectic form of this space. I don't really need to consider G action here, but I want action of a torus. So let's have action of C times on V subject to our condition, such that T applied to omega is T squared omega. Well, for example, we can take T applied to V is T to minus 1V for any V. Now, and also we have a very simple choice of nabla, namely, how to say this, tautological connection on a vector space. And so we produce a star product, and this is what is called Mayal while star product. It can be given explicitly, namely, so let P, which is usually denoted by omega to minus 1, is a Poisson bivector. And I can consider this map as a bidifferential operator. This is just contraction. Then there is a very
But why are there two functions in the image?
well, what you do here, well, here you have, I consider this as symmetric algebra of V dual, and then P is an element of the square of V, and then I contract. Well, one can write a formula, so if you somehow, if you have d over dx times d over dy, and you want to apply this to a function f tensor g, well, we of course have df over dx. Well, and that's a shorthand notation for this. So Poisson bivector is a sum of these gadgets. And then when I apply this Poisson bivector, this means this derivation. Okay, and now there is a formula f star g equal to mu. I will explain what mu is. X HP over 2 applied to f times g. And mu is nothing else but multiplication. Well, in particular, one can notice well, since, well, given fg, there is large enough n such that p to the n of f times g is 0. Well, this p is just some, some differentiation. We see that the star product of f and g, it's not a formal power series in h bar. It's a polynomial. All high enough by differential operators kill this f and g, this particular f and g. There is no universal choice. And what we can do, well, we can now take some complex number and plug it instead of h bar, instead of formal variable. Well, I could take Planck constant, but I'm not a physicist, so I would rather take 1. So we now define f star 1g, by definition, is sum from I equal to 0 to infinity di fg. That's a new associative product on this algebra of functions. But it's not that new. It's a very well-known product. So this algebra, CV with this star 1, is nothing else but the Weil algebra. Of the dual vector space of V tilde. So let me recall what the Weil algebra is. Well, I denote it with bold A of V tilde of V dual is the quotient of T of V dual by, well, U times V minus V times U minus P of UV. And actually, we have encountered this algebra during the school already. Namely, we can take Lagrangian subspace, gamma, say V naught in V, then this Weil algebra becomes isomorphic to the algebra of differential operators on V naught. It's an easy exercise. Okay, that was the first example. And now two more complicated. Well, let's take G reductive group. And X is a cotangent bundle of G. We have action of G times G here. And this G times G is our new reductive group. And also we have an action of torus. The most obvious one by rescalings. So T applied to G1 alpha is G1 T2 minus 2 alpha. Then I take some symplectic connection, nabla. And produce a star product. So what do I get? Well, again, like in this example, the star product is actually polynomial. And to see this, well, we note that grading.
Do you mean G cross C star or G cross T cross T star?
Oh, yes, thank you. G cross G, like this, yes. Now, so grading on Cx is non-negative. And then di decreases degrees. And this again implies that product of two functions is polynomial. So we can again plug whatever number we would like instead of h. And it turns out that Cx with this new star product is just algebra of differential operators on G. The standard quantization of the cotangent bundle. Okay. Well, it's not so easy to see. Actually, there is a sort of an explicit isomorphism constructed by some physicists for whatever purposes. But one more remark here. Actually, if we take invariance with respect to left action, and this left invariance is the algebra of regular functions on G dual. And now we have a new associative product on this G dual. So first of all, we get star product on algebra of polynomials with coefficient with C of G dual. And then we get star 1 on C of G dual. Well, from what I stated here, it's clear what this algebra is. This is just U of G. Universal enveloping algebra of G. And now finally, our third example, which looks very similar to this one. And that's actually an example I want to deal with. So finally, we take X to be equivariant Losev slice. And we have our G action, and we have T times action. Then we choose connection and produce star product. Well, as I noted before, this the algebra of functions on X is not positively graded. But anyway, the product of two functions is polynomial in H bar. But anyway, the algebra of invariance here, which is algebra of functions on this Losev slice, is positively graded. So we got all this construction. We get this star sub 1. And I call this algebra curly W. This is by definition. And this is W algebra. Now, well, it turns out, of course, to be isomorphic to W algebra introduced by Primit. But anyway, let's notice that we have completed our original program. We have quantized the algebra of functions on the Losev slice. So from construction, W is quantization of Losev slice of C of S. So it wasn't so obvious for premise construction, but here it's more or less clear. Okay, so the next time I will try to prove something about algebras I introduced. In particular, I'm going to somehow sketch the proof that this two construction give the same answer, which is not clear from the discussion above, and also I will try to explain why Scriabin's theorem holds. And just a few words, and perhaps that's the main explanation why W algebras are useful. So somehow S was a slice to the orbit O in the algebra of functions on G dual, and it had very clear geometric meaning. Just that tangent space is the direct sum of tangent spaces to these two guys. But now W is slice to O in UG. And basically, the next lecture in the next lecture, I will try to explain what is precise meaning of this. Well, that's all for today. Thank you.
So if I understood your discussion with the T's, I can view, it says that this quantization is actually somehow the unique graded quantization.
Unfortunately, it's not. So, okay, let me explain something. Well, if we try to quantize this algebra, then no, its quantization is not unique. And the reason for this is rather stupid. Of course, I should have mentioned this on the first lecture, but the first example of W algebras was actually due to Constant, and he dealt with principal elements. And in the case of principal element, this algebra, this Poisson algebra, is commutative. the Poisson bracket is 0. Actually, this algebra is the center of this, and W algebra is the center of this. But once you have a commutative Poisson algebra, you can quantize it in many, many different but stupid ways somehow. So there are very many quantizations.
But up to equal, I mean,
Even not up to equivalence. You can get more commutative quantization. You have commutative quantization, the most natural one, and many non-commutative ones. Well, so for $10, I will construct you an example. But please believe me, there are quantizations. What one can say is that if you try to quantize this x, then you get a unique quantization. Unique G-equivalent quantization, at least.
I'll have to ask you. I'm confused about some.
Okay.
But
So
I mean,
$10 is not too much.
two coming from this, but also quantization will be closely related by this. And Arun, maybe is this?
I mean,
But you have a
these quantizations are classified by some H2.
Yes.
And from what I understood, that you were saying that there was a unique class that I can put my fingers on.
Yes.
How
Quantization
do you
of
understand
x.
that uniqueness?
It's
Of
quasi
X.
symplectic.
So-
Here, symplectic, you assume there is a non. When you say you take the zero Poisson, I mean here you assume that you have a symplectic form, non-degenerate.
Yes. And quantization of x is unique precisely by the reason you mentioned. H2 is equal to 0. But for quantization of situation with quantization of Poisson, of arbitrary Poisson varieties, is much more complicated.
So this W becomes unique once I consider the symplectic.
Once you consider this, so yes,
I
symplectic variety.
understand.
There are no more questions? Let's